Chapter 4, the processor. In chapter 1, we explained that the performance of a computer is determined by three key factors. Number 1, instruction count, clock cycle time, and number 3, clock cycle per instruction or CPI. Similarly, in chapter 2 explained that the compiler and the instruction set architecture determine the instruction count required for a given program. However, the implementation of the processor determines both the clock cycle time and the number of clock cycle per instruction. In this chapter 4, we construct the data path and the control unit for two different implementation of LEG V8 instruction set. This chapter contains an explanation of the pipelines and techniques used in implementing a processor, starting with a highly abstract and simplified overview in this section. It is followed by a section that builds up a data path and construct a simple version of processor sufficient to implement an instruction set like LEGV8. Later in this chapter, we cover a more realistic pipeline LEGV8 implementation, followed by a section that develops the concepts necessary to implement more complex instruction set like x86. We will be examining an implementation that indicates a subset of the core LEGV8 instruction set which is the memory instruction load register, unscaled LDUR, and store instruction unscaled STUR. The arithmetic logic instruction add, subtract, and or, and the instructions compare and branch on 0, CBZ, and branch B. This subset does not include all the integer instruction, for example, shift, multiply, and divide are missing. Nor does it include any floating point instructions. However, it illustrates the key principles used in creating a data path and designing the control. The implementation of the remaining instructions is similar. In chapter 2, we looked at the core LEGV8 instructions, including the integer arithmetics, logical instructions, the memory reference instructions, and the branch instructions. Much of what needs to be done to implement these instructions is the same, independent of the exact class of instruction. For every instruction, the first two steps are identical. First step is send the program counter PC to the memory that contains the code and fetch the instruction from that memory. Step number 2, read one or two registers using field of the instruction to select the registers to read. For the load and CBZ, LDUR and CBZ instructions, we need to read only one register, but most other instructions required reading two registers. After these two steps, the action required to complete the instruction depend on the instruction class. For each of these three instruction classes, which are memory reference, arithmetic logical, and branches, the actions are largely the same. Independent of the exact instruction, the simplicity and regularity of the LEGV8 instruction set simplifies the implementation by making the execution of many of the instruction classes similar. For example, all instruction classes except unconditional branch use the arithmetical logical unit ALU after reading the registers. The memory reference instructions uses the ALU for an address calculation, the arithmetic instructions for the operation execution, and conditional branches for comparison to 0. After using the ALU, the action required to complete various instruction classes differs. A memory reference instruction will need to access the memory either to read data for a load or write data for a store. An arithmetic or load instruction must write the data from the ALU or memory back into the register. Lastly, for conditional branch instructions, we may need to change the next instruction addresses based on the comparison. Otherwise, the PC should be incremented by 4 to get the address of the subsequent instruction. This figure shows the high-level view of an LEGVA implementation. Also, this figure shows two important aspects of instruction execution. First one is that in several places, uh, data going to a particular unit as coming from two different sources. For example, the value written into the PC can come from one of two adders. The data written into the register file can come from either the ALU or the data memory. And the second input to the ALU can come from a register or the immediate field of the instruction. In practice, these data lines cannot simply be wired together. We must add a logic element that choose from among the multiple sources and steers one of those sources to its destination. This selection is commonly done with a device called a multiplexer. Uh, Multiplexers are also called as a data selector. Second aspect is that the units must be controlled depending on the type of instructions. For example, the data memory must read on a load and write on a store. The register file must be written only on a load or an arithmetic logic instruction. Similarly, the ALU must perform one of these several operations. This figure shows the required multiplexers and also control lines for the major functional units. A control unit which has the instructions as an input is used to determine how to set the control lines for the functional units and two of the multiplexers. The top multiplexer which determines whether PC plus 4 or the branch destination address is written into the PC is set based on the zero output of the ALU, which is used to perform the comparison of a CBG instructions. The regularity and simplicity of the LEG V8 instruction set means that a simple decoding process can be used to determine how to set the control lines. In the remainder of the chapter, we refine this view to fill in the details which requires that we add further functional units, increase the number of connections between units, and of course enhance a control unit to control what actions are taken to different instruction classes. In this first design, every instruction begins execution on one clock edge and completes execution on the next clock edge. To discuss the design of a computer, we must decide how the hardware logic implementing the computer will operate and how the computer is clocked. The appendix A of this book gives a brief background in digital logic. So, the data path elements in the LEGV8 implementation consist of two different types of logic elements. Number one, elements that operate on data values, and number two, elements that contains state. The elements that operate on data values are called combinational, which means that their output depends only on the current input. Given the same input, a combinational element always produces the same output. The ALU is an example of combinational elements. It always produces the same output because it has no internal storage. Secondly, other elements are not combinational but instead containing state. An element contains state if it has some internal storage. We call these elements state elements because if we pull the power plug on the computer, we could restart it accurately by loading the state elements with the values they contain before we pull the plug. Furthermore, if we save and restore the state elements, it would be as if the computer had never lost power. So these state elements completely characterize the computer. The instruction and data memories as well as the registers are all examples of state elements. So combinational elements and the elements that operate on data values are all combinational, which means that their output depends only on the current inputs. Given the same input, a combinational element always produces the same output. AND gate, adder, multiplexer, and ALU all are examples of combinational elements. The state element has at least two inputs and one output. The required inputs are the value, data value to be written into the element and the clock. The clock determines when the data value is written. The output from state element provides the value that was written in an earlier clock cycle. For example, one of the logically simplest state element is a D-type flip-flop, which has exactly these two inputs, a value and a clock, and one output. In addition to flip-flop, LEGV8 implementation uses two other types of state elements, which are memory and registers. The clock is used to determine when the state element should be written. A state element can be read at any time. Logic components that contain state are also called sequential because their outputs depend on both their inputs and the contents of the internal state. For example, the output from the functional unit representing the register on depends both on the register number supplied and on what was written into the register previously. A clocking methodology defines when signals can be read and when they can be written. It is important to specify the timing of reads and writes because if a signal is written at the same time that it is read, the value of the read could correspond to the old value, the newly written value, or even some mix of the two. Computer designs cannot tolerate such unpredictability. A clocking methodology is defined to make hardware predictable. For simplicity, assume a, let's assume an edge-triggered clocking methodology. An edge-triggered clocking methodology means that any value stored in a sequential logic element are updated only on a clock edge, which is a quick transition from low to high because only state elements can store a data value. Any collection of combinational logic must have its input come from a state set of state elements and its output written into a set of state elements. The inputs are values that were written in a previous clock cycle, while the outputs are values that can be used in the following clock cycle. Figure shows the two state elements surrounding in a block of combinational logic which operates in a single clock cycle. All signals must propagate from state element 1 through the combinational logic and to state element 2 in the time of one clock cycle. The time necessary for the signals to reach state element 2 defines the length of the clock cycle. Control signal are signal used for multiplexer selection or for directing the operation of a functional unit. Contrasts with a data signal which contains information that is operated on by a functional unit. For example, if a state element is not updated on every clock, then an explicit write control signal is required. Both the clock signal and the write control signal are inputs, and the state elements is changed only when the write control signal is asserted and a clock edge occurs. The word asserted to indicate a signal that is logically high and assert to specify that a signal should be driven logically high, and deserted to represent logically low. We use the term assert and desert because when we implement hardware at a time one represent logically high and at time it can represent logically low. A reasonable way to start a data path design is to examine the major components required to execute each class of LAGV8 instructions. Let's start